Good evening, everyone. On behalf of India Space Labs, I warmly welcome all the participants to today's session of Summer Internship and Training Program 2026. It is my privilege to introduce our speaker, Ms. Akriti Ma'am, a control engineer in the aerospace domain with her MTech from IIT Bombay. She has worked on various aerospace projects and brings valuable technical expertise to today's session. Ma'am, we are honored to have you with us today. Kindly, I request the students to kindly maintain discipline and turn on your cameras. A Q&A session will be held at the end. With this, I invite Ms. Akriti ma'am to take this session forward.
All right. Thank you for the introduction. Hello everyone. Hope you had a great weekend. Let's begin with our session. So, today's session will be something different from what you get to know in the terms of drone technology. So, hopefully, you'll enjoy the session. So, give me 2 minutes. I'll share the screen and then we'll begin. All right. Hope I'm audible. My video is clear and you can see my slides. So, so today we'll be focusing on what in the drone terminology or in any aerospace sector we call it as drone guidance, navigation, and control. So I'll tell you, in the subsequent slide what all these means and how these are applicable for the drone purpose. Right. Before we begin with the today's 2 hour session, there's an important announcement that actually the drone is a very vast field, and the topics that I'll be covering today is just to make you familiar with various aspects which actually works in the software sector of the drone. That means yesterday I discussed about the flight controller. Now there are some standardized flight controllers that are available in the market, but this is something that if you're designing your own drone with own algorithms, these are some of the things that you have to remember while you are creating the software. So these are just making you familiarize with the concepts that works in the field of drones, right? So if you want to write something, you just grab some pen and paper and whatever you feel like where you can write, and hopefully you'll learn something new today in today's session, right? All right. So now let's begin with our first section, that is about the world of autonomy. So what do we mean by autonomous drone? Yesterday I distinguished there are two kind of way that we can run our drone. One is remote control based. The one that you have seen people are playing around with, right? They have a remote control in their hand and they are flying their own drones. But there is another sector wherein actually what industry works upon creating an autonomous drone, right? So what do we mean by autonomous drone? There are some set of sensors I told you, accelerometer, gyroscope, all those sensors. These kind of sensors are there inside the drone, and then it makes a decision what to do next. Say for example you have an obstacle that is placed in front of the drone. Now drone will be able to detect this is my obstacle, I have to cross this. So it will stop there, it will take some other path and it will go. So for that purpose we have the autonomous drone, right? So yeah, so these are the drones that operate independently and they do not require any constant human intervention. It can take a decision on its own. Say for example, it is flying at a very high altitude, and now you say, say for example, it's too high. It's not the battery power is very low. Now it can take a decision. Okay, my battery is low. I should return safely back to my initial position or my home location. So that way, these autonomous drones are capable of performing the task like whatever they want to do. Maybe if it is a Amazon air delivery, it will go to that location, it will detect I'm at that particular place, and it will drop the parcel, and it can navigate through the environment automatically, right? And it relay on the sensors, AI, and algorithm. So, why do we see that the autonomy is hard? Why, working on this sector is a bit hard, not possible, a bit hard, right? So we have to admit this fact that we live in an uncertain world. Now, what do I mean by uncertain world is there are sensors that are noisy. What do I mean by noisy is it is not like that if you are at 10, say for example, you have a drone and you say, okay, my sensor is saying I'm at 10-meter altitude. No, it doesn't give you the reading like this. How it gives the reading? Sometime it will be reading 10.1, 10.5, 10.2. This kind of what do you call, the data is something that you get from the sensors, and then it is difficult to get that what is the actual altitude of my particular drone. So that is why the sensors are noisy. That is what we mean by a noisy sensor. Then there might be delay in the motor, right? Say for example, you said increase the speed of my motor. There will be some even zero point 0.5 second of delay in the motor can cause a huge difference. That is why it is important to accept that this is the uncertainty that we have to face, right? And there are some external disturbances, right? So if the sensors are noisy, there are some winds that are going on, and physics doesn't care about the code. Physics just say that okay, I have to, if my speed is increased, I have to go up, my speed is decreased, I have to go down. It doesn't care about whether there's some wind, there's some delay in the motors, based on the command that you're giving, or the sensor is not giving any correct value. It will just do what it has to do. It doesn't know what you're trying to do. So that is why this autonomy problem is split into three parts. Just remember that, or make a note of this, that autonomy have three components to work with, right? So first component that comes is the navigation. That is the know state, like knowing what state you are, right? Then comes the second part, which is guidance. That is deciding the motion, how you will be traveling from one point to another point. And then comes the control. Control means whatever navigation and guidance you have given, how I will be controlling my drone such that my mission is fulfilled, right? So these are the three parts. We will further understand a bit more about it. We'll explore more about what is this navigation, guidance, and control. But for now, this is what the big picture is all about, wherein the autonomy is being the problem is being split into three parts, right? And why there are three parts? For the modularity purposes. Like say for example, you upgrade the GPS with changing PID controller, right? So for why you're upgrading the GPS for the navigation purposes, and you're also changing the PID controller that comes into the control part, right? So at same time, you are able to address the problem separately. Maybe the navigation problem you are addressing separately, control problem differently, and guidance problem differently. So that way, the things becomes a bit dissecting, such that we are able to understand the problem easily, and work on it step by step, right? So this is the basic flow of autonomy. You can just take a screenshot, or you can just note it down, but actually the autonomy, how the autonomy works. So just come here first. So first comes the sensor, right? Okay, we'll take a scenario, and we'll work on that step by step. First comes the sensor. What sensor does is it knows what is your current position, orientation, how much acceleration is there, how much velocity is there. All this information is taken by the sensor. Then comes the navigation. In navigation, we said, okay, I'm currently at this position. I want to I want to go at some point B. Say for example, you're sitting at your home, that's point A, and your college or your office is at the point B, right? So now I want to go from home to college or my office, right? So that comes point B. So that comes the navigation, right? We have selected like where we want to go. So that is why here we have written navigation tells you where you are. You just get to know your point, right? Now the guidance tell about where to go, right? The point B that we are selecting, that comes like where to go, right? How we will be going. That is something guidance will tell you, right? How we will be going via bus, we'll be taking some, maybe for example, MG Road, then Church Street, and then we'll be able to reach our college or office. So that is what guidance tells you about. And control tells you about, okay, I'm at this point, I have to go at this point. How will I turn? I have to turn this way, then I'll go straight, then I have to take a right turn, I have to go straight. So the controls that I use, the motors, how those motors and propellers will work. So that comes under control, and these control instructions are being given to motor and propeller, and accordingly, it to roll, pitch, and yaw, the one we just discussed yesterday, and then you're able to trace the path, right? So got the basic flow of autonomy. It goes from sensor to navigation to understand where am I, then the guidance, where to go and how to go, then come control, how we will be moving, how will be my motors and propellers will be moving, and then finally the motors and propellers which will drive your drone, right? So that is how autonomy actually works, right? So hope this is clear. Let's proceed further, right? So if you didn't understand, I'll just explain with a simple space mission analogy, because since we all are here to understand about space, so little bit of space analogy we can understand from here. So first comes the guidance part, wherein we have a rocket. You might have seen some rocket launches that goes on. So what we are trying to do there, there's a rocket. We are aiming a spacecraft by controlling the direction of its rocket thrust at launch or other timing, right? So we design a path for our particular satellite. So say, for example, a rocket will go like this, it will separate with the satellite, and then satellite will perform its action, right? Then comes the navigation part, right? So navigation, what it is telling, getting from one place to another while in space. This often involves long period of coasting and short bursts from small rocket to change course. What it means by here is, when we are in space and a satellite is moving, we have to go somewhere. Now there might be chances that its course might be incorrected. So there are some thrusters that are available over here which helps it to correct its course. The direction it is going, it corrects its course. So that is how in satellite it works, and how we are controlling it. So for controlling how we are changing the orientation, how we have to tilt ourselves, so that all comes in the control part. So that is how guidance, navigation, and control actually works in space mission, right? So lot talked about the introduction part. Now let's dive into these small parts, right? So first comes the navigation. So how the drone knows its state, like how the drone is able to know what state it has to go, right? So before we go into the navigation part, there are some basic concepts that you need to understand, and then we'll dwell into the navigation phase, right? So this is something that you would have already studied in your previous class, wherein you have a body frame and an inertial frame. Say, for example, this is a boy. It is moving in this particular, cart or box, whatever you want to say. So for this particular, you know, boy who is standing over here, for him, it feels like he's standing still. He's not moving, right? You also feel the same thing. Like say, for example, you are in a train, you feel like I'm sitting, I'm not moving. But for the person who is sitting outside the train, that person will feel, okay, this person is moving, it's moving with the train, so it's moving, right? So what is happening over here is, this comes under the body frame, right? In the body that is moving, and inertial frame is something which is at the global level, right? So which you can you're seeing from the outside, and body frame is the frame with with the which your body is moving. Similarly, In case of our drone, we have an inertial frame and the body frame. So inertial frame is something that we measure with respect to the earth, and the body frame is something that happens with respect to the body, right? So all the rotation, all the position change which happens with respect to the your particular drone, that comes under the body frame, right? So for body frame, we have these three orientation. One is the roll, pitch, and yaw. So this roll, pitch, and yaw that we studied yesterday, these comes as the orientation in the body frame, correct? And inertial frame is something that is seen from the outside. Maybe something that you are seeing towards the drone, that comes as an inertial frame. You become an inertial frame for the drone, right? Okay, so in the beginning of our navigation, I said there is something known as state. So, what is state? State is nothing but the positions and velocities that we were discussing about, right? So, for in simpler terms, you can understand that there are 12 things that define flight. Flight means like there are 12 parameters that will help you to understand the entire drone, what it is doing, at what position it is. For that purpose, we have 12 numbers. The first one that comes is the position. Obviously, knowing the position of the drone. So where my drone is there in the 3D space, that comes as a position. So this constitutes three states or three numbers, x, y, and z. Then comes the velocity, how fast the drone is moving in each direction, right? So how fast it is moving in this direction, then maybe in y direction or in z direction. So just to clarify, this direction along the UAV, we call it as x direction. The one that is along this wing, we call it as y direction, and the one which is cutting the drone in the vertical direction, that we call as z direction, right? Just remember this. This is the x direction along the UAV, y direction along the wing, and z direction along the perpendicular to this x and y, right? So that is how we define the states, right? So UV and W, we call the velocities as UV and W. Then we have the orientation. Orientation means how much it is tilted, how much is my pitch, my roll, my yaw. For that purpose, we have three more states known as roll, pitch, and yaw. That's our orientation. And then we have the angular rate. So angular rate is nothing but the angular velocities. So PQR, how fast it is rotating in each direction. Now we need to understand also. Say for example, you have some drone, and maybe it's changing its angle, but the rotation is very slow, right? So that means that the correction will be very slow. So that is why maybe we have to increase the angular rate. So we say that we want it fast, right? So that is why these angular rates, knowing these angular rates are also very important. How slowly or how fastly it is rotating, right? So these are the 12 states. First three comes the position, knowing the location. Then comes the velocity, how fast it is going in x, y, and z direction. Then comes the orientation, and then comes the angular rate. Angular rate is nothing but angular velocity, right? So these are the 12 parameters that define the the states of the drone, right? So coming up to the sensor part. So sensor yesterday, this small revision with what we did yesterday and what we have to cover today. So first comes the navigation sensor. So what this navigation sensor is doing is, like, it is measuring the angular rate and the acceleration, right? So you remember that for yesterday in IMU, I told that IMU consists of accelerometer, which measures the acceleration, and gyroscope, which measures the angular velocities, right? So that is what I have written over here, that it measures the angular rate and acceleration. And there is something known as update rate as well. So for as an drone engineers, we need to understand at what rate it is getting updated, right? So how fast is my data coming to me? So in a simple term, that you can understand as an update rate, right? After how many seconds, how many milliseconds are my is my date getting updated, right? So that is required for the stability purpose. Like, so say for example, I have a drone over here. Now I'm saying that my update rate is somewhere 2 seconds. So what will happen? Say my drone is here, and after 2 seconds it is there. You understand what happened? After 2 seconds only, I'm getting to know that my states got updated or my angle acceleration got changed, right? So that is why our update rate has to be fast, right? So for that purpose our devices has to be fast, right? So where, for example, if it is 200 hertz, so in 200 hertz, after maybe approximately around zero point 0.5 seconds only, you will get to know, okay, from here it went here, right? Just small, and after 2 seconds we know that how it is tracing the path. So hope you got the point that why this update rate is very very important, right? So yeah, so that is something that we require for the stability purpose. And then errors we get as sensor bias, electrical noise, and misalignment. You know, all right. So we'll understand all these things, but first let us look at the video. So what you are seeing is that person is having an IMU in his hand. So based on how it is rotating it, you are able to see the measurement. So on his screen, he is able to get how much angle it is rotating. Right. So now he's trying to give the acceleration in Z direction to understand. And this C is giving in X direction. So you can observe here it was getting changed, right? So this is how actually you're able to, with the help of IMU, you're able to know, because this IMU is attached to your drone, and then if the drone will move, this IMU will also move. So that is how these things work. And that is why the update rate is important, so that there is no delay in the data that is coming to us, right? So errors I was talking about, one is the sensor bias. Probably the value that it is giving is something different than the actual current value. So that is what is known as sensor bias. Then we have the electrical noise. Electrical noise means since there are a lot of circuitry involved, there might be some interlinking between there might be some electromagnetic induction or something that might induce the electrical noise. And then the misalignment, maybe you have rotated your IMU in some 45-degree, but it's still showing you it's 0 degree. So there's some misalignment also that can happen, right? All right. So what I just showed you was one of the sensors. Now there are some additional sensors also that are attached to the attached along with the IMU, right? So IMU is a different component, and these components are also different. So the first one we'll discuss about is the magnetometer. So magnetometer is actually used for knowing the heading, right? So now you will ask a question that if IMU is able to give us the angular rate, from there we'll definitely get to know the orientation, right? What is the orientation? Roll, pitch, and yaw. So why do we need the magnetometer additionally? So the answer to this is the redundancy. So there are a lot of errors that are involved with the IMU. So when you don't say, for example, you go to a doctor, and doctor prescribe you such and such medicine, which you are not aware that whether that doctor prescribed a set better medicine or not. What you will do in that case, you'll go for a second opinion, so that you want to see that whether the first doctor what it was saying, whether it is comparable to what second doctor is saying. So in the similar way, we have to ensure that whatever data that we are getting, whether it is correct or not. For that we have the magnetometer. So what magnetometer does is, uh, based on the magnetic, like the way our magnetic compass works, it works in the similar way in order to get the heading correct. So for that purpose we have the magnetometer, right? So the update rate, it updates at 50 to 100 hertz, and this was updating at 200 to 1000 hertz, right? So that is the difference. So this is in terms of update rate, this is comparably a bit less, but it works, right? So this is one kind of sensor. The another sensor that we have is the barometer. So what barometer addresses is the altitude. I told you about, by the change of the atmospheric pressure, we have the change in the altitude. So for that, this barometer works, right? And it has the update rate of 10 to 50 hertz. So this is something which is the characteristic of that particular system. If you can get a better system which can update maybe slightly better, in the minimum amount of time, then it's better to have such kind of sensor, right? And okay, so we'll understand in the upcoming subsequent slides also that why the update rate of this is low, whereas the update rate of this is high, right? So you'll get to know that why these update rates is very, very crucial for a system when we are building a drone, right? And the third one that you all know that we have in our phones as well is the GPS. So this kind of GPS system is what it looks like. So it helps to get you the X, Y, and Z positions, right? And it has much lower update rate, that is 1 to 10 hertz, and it helps in correcting the long term drift, right? All right. So we were talking a lot about the update rate. This should be slow, this should be fast. Right. So there are a lot of components, like IMU is there, right? IMU have a different amount of update rate. Barometer, they have a different amount of update rate. GPS have different amount of update rate. Now how will I synchronize between all of them? It will be difficult for me to synchronize then. This is updating in 1 millisecond, 20 millisecond, 200 millisecond. It will be difficult. So and it is not like we can rely on only one thing and we cannot rely on other thing, because ultimately we have a lot of 12 parameters or 12 states. How we will understand who is working at what rate, how we will control it and all that. There's a lot of juggle that is involved, because there are a lot of different sensors that we have to use with a different update rate, right? So now we are trying to understand that why sensors alone are not enough. We cannot only rely on the sensors. When comes the sensor noise, that is, sensors are never perfect, right? That we also understood in our introductory slide. Then there is an integration drift. Okay, so this will be covering up, upcoming. But I currently discussed about there is some delay and bias due to which we have to wait a lot. Say for example, GPS is updating at around 200 millisecond. So now IMU have to wait for a very long time, for around 200 steps. It have to wait such that it can get the GPS value. You're understanding? It's so for that purpose, it is not able to synchronize between each other. And for that purpose, we have the sensor fusion, right? So look over here. We have IMU over here, and then we have a GPS over here. Both are doing the same thing. IMU is also giving me the position, GPS is also giving me the position. Now you will ask, IMU to give the acceleration, it does not give the position. But when you integrate, you would have done in your previous classes in the kinematic equation, you would have seen if we integrate the acceleration, we get the velocity, and we when further integrate the velocity, we get the position. So IMU is also capable of giving the position. GPS also gives the position, right? But the update rate of both is different, right? It gives a fast update rate, it gives slow update rate. But I cannot rely on one particular IMU. I cannot say that, okay, this is fast, so I can rely on this. Maybe this is giving a wrong value. This is GPS is giving a right value. For that purpose, for all this khichdi that is created, for that purpose, we have the sensor fusion, wherein you fuse the data of two sensors that is coming, and you estimate. What I said is estimate. You estimate what would be the true value, or what would be the exact value. I should not say the exact value, what would be the approximate value of my X, Y, and Z. Hope that is clear. I'll repeat it once again. What is happening is I'm getting the position from IMU. I'm also getting the position from the GPS, right? Ignore the magnetometer for some time, right? But the problem is that IMU, though it is fast, but it has a drift, right? It can, give the data fast, but there are some errors that are involved. But GPS, on the other hand, is slow but gives the accurate data. So how will I get to know that what's my actual position? For that purpose, we have a concept known as sensor fusion, which takes the data from both the sensor and based on what is the accuracy, what is the update rate, some mathematical calculation is done such that we get the approximate location, which is almost approximation to the true value, right? For that purpose, we have the sensor fusion, right? And sensor fusion concept is very very important in the in the drone industry, since this is something which actually helps you give the accurate data, and the more accurate the data you get, more properly your drone works. So that is why sensor fusion is very important, right? So hope you got to know. If you have any doubts regarding this, we'll clarify in the Q&A section, right? Okay, I told about the sensor fusion right now. So that this comes under this Kalman filter concept, right? So then we have a extended Kalman filter. It is a mathematical tool that predicts the state and corrects it whenever new data arrives, right? So that correction is being done by the Kalman filter. So from filter only you understand it's some kind of filter that is there so that the noisy data can be removed, and maybe we get the correct data based on the data that we are getting. So navigation is intelligent sensor fusion, right? So let's take a small break after learning a lot about this, and probably you can you know you can just have a small revision after what we have done, right? This is a small quiz, so you can test yourself, and probably I'll also help you in this. So which sensor provides the absolute position? Absolute position means XYZ. And what we said, that is being done by the GPS. Correct? Then question 2. Why do we fuse the sensor data? Right? So these are the three options. And the correct one is it reduces the noise and corrects the drift. And then what is the typical IMU update rate? So it is around 200 to 1000 hertz, and the control acts on the estimated state. That is true. So why I'm saying that control acts on the estimated state? Because right now only we understood the concept of the Kalman filter, wherein sensor fusion is being done such that we get the estimated state, and state means all the position, acceleration, velocity, angular velocity that comes under the state, right? So these are the, hope you would have understood about the navigation, and let's proceed towards the next section that comes the guidance. You remember for the autonomy, we said the problem is split into three parts. One is the navigation, guidance, and control. So now you understood about the navigation, wherein we had a lot of sensors which used to tell about our states, right? So now we want to go from one place to another. How we are going? That comes under the guidance part. All right. So what does guidance do? So what I have written is it translates the high level command like loiter here. Loiter means that you just hover at that particular position, fly at waypoint P, return to launch into mathematical objective, right? Say for example, you have a delivery system that is going on, and you said from this station I have to first go to this house, then I have to go to this house, then I have to go from here to here, from here to here, and back to this house, and then back to my warehouse. So for each and every drone, this kind of structure is being created. And and although I'm telling you everything in terms of theory based, but actually it is done with the help of the mathematics. which we are not covering over here. The whole sole idea of the lecture is to give you some points that you remember, such that while you're developing your drone or while you're working in the drone industry, you have some idea like how these things actually works backend, right? So hope you would have got some idea from this picture, like how all the guidance or all the pathway is being created, like how to go from one place to another, right? It generates the target states for the controller to chase. Say, for example, target position, desired velocity, and attitude. Right? So, guidance is acts as a strategist. Like, okay, you go there. Okay, wait right now. Okay, do one thing, you come back. Right? So, that is something which guidance does. Right? It doesn't fly the plane, it decides the path. Okay, so guidance means the path. In a nutshell, you can understand in this way, right? So it's the same way that you're choosing, a path on Google Map for less time and minimum traffic. Like this, maybe this path would be having a lot of traffic. Probably you can, go from this path. So that is what guidance is doing. Okay, so in the drone terminologies, okay, I was talking about in layman language, but when it comes to drone, how these commands actually work, right? So what are the different terminologies, you can write it down also, which which is used in the drone to understand what guidance command has been given to that particular drone, right? So the first one that comes is the hover at point, which in technical term we call it as position hold. So naturally from the terminology only you are able to understand that we are holding the position of the drone, right? It maintains the XYZ coordinates and guidance outputs zero velocity reference. So to the from the guidance we get to know guidance says okay, I have to hold this position and my velocities should be zero. So this is how the guidance gives the command, right? I only said that hover at that point, right? You just hold the position over there. What does guidance give? Guidance says, okay, you told me no that hold the position. Okay, do one thing for me. This is something it says to the controller. Do one thing for me. You hold the XYZ coordinate, whatever coordinate were there previously, hold it for me, and make sure that the velocities are zero. That is something guidance is telling to the controller, right? So I hope the scenario is clear how guidance is telling the states, the navigation states that I discussed upon, right? So then comes the fly to waypoint. That is the target seeking, basically going from one location to another and from that location to that location, right? So over here, if you observe, first we are at 164 feet. I said from 164 feet go to 130 feet, right? And then from 130 feet to 164 feet. So that is what target seeking is doing. It is generating the velocity vector pointing from the current position to the target, right? So that is how seeking is being done. So accordingly, the states are being given to the controller. Okay, this should be my velocity, and this is how I want to go. Right? Just a second. All right. So next comes the follow line, which is the path following. So from the statement itself, you can understand path following. There is some path, and I'm trying to follow over there. So you might ask, what's the difference between seeking and path following? So the difference is here we are defining only the waypoint. Waypoint are the points, right? So for example, you want to from here you want to go to Taj Mahal, then you want to go to Qutub Minar. I just said this, right? So these are my waypoints. This Qutub Minar and Taj Mahal, these are my waypoints, right? Similarly, in the path following, I am not saying I have to go to Qutub Minar. That's a different thing. I said I want to go from here, take a left, and I have to go there. Okay. So that comes under the path following. See, this is my path that I have to follow. For that purpose, the different set of guidance commands are given. Right? It tries, and what the drone tries to do, it tries to minimize the cross track error. What do you mean by cross track error? The error between my path and the drone. So this error I have to minimize. I have to stay on my path, right? For that it is written minimize the cross track error to stay on the straight path between 2 points, right? So it doesn't mean the straight points like the line. The straight path means whatever path is being created, so slowly and steadily its points are increasing. So that way it have to maintain the path. In a simple word, just understand that much. Path following means just stay on the path. It should not diverge from the path. But here if you see, I have not defined any path. I just defined from this point to this point a straight velocity vector. That's it. Correct? And then this is the simpler one, which is known as maintain altitude, which is the z-axis hold. Right? So I will just want to maintain the altitude. Maintain altitude means my distance has to be same, but I can roam around anywhere. My distance with the earth has to be same, but I can do anything in x and y direction. So that is the maintain altitude, right? So it adjusts the vertical velocity to keep the barometer. Remember, barometer helps to give us the height and GPS height. GPS height means, from GPS we are getting X, Y, and Z coordinate. So Z coordinate of the GPS or the or the measurement from the barometer, that has to be constant, right? So these are the guidance command, right? So how does this guidance logic works, right? In mathematical terms, in mathematically, it's simply just doing one thing. There is some target value and there is some current value, and target minus current gives us error. And what guidance is trying to do, it is trying to minimize the error. How it is trying to minimize the error? It is saying, okay, I want to minimize the error, make my velocity to 10 meter per second. So that is how this guidance is commanding that I want to reduce, do that. But understand this thing, guidance outputs desired motion, not the motor command. It doesn't say that. You would have heard me saying, this velocity, this position, but I never said that, okay, tell my motors to increase the speed or decrease the speed. That is not what guidance does. Guidance just says, okay, if I want to go from this point to this point, give me this velocity, give me this acceleration, give me this position. So this kind of logic is something that is telling to the controller, because next we are moving to the control. So this is something it's telling to the controller. Ki, this is I want to do. But controller is something which will tell the motors, ki, okay, I'm getting this command. You do such that you increase your speed such that I'm able to achieve this velocity. So hope you understand how I'm trying to say. I'll repeat it for you. What guidance is doing is, guidance is just saying, okay, I want to go from this point to this point. You increase the velocity. And what controller is saying, motors, you increase the velocity. Sorry, motors, you increase the speed, increase the rotation of your speed such that I'm able to achieve the velocity that is given by the guidance, right? So this is how all the systems are working systematically. Guidance is giving some commands to control, and control is giving some commands to the motor. So this is step by step. This is something that is happening inside the drone, which you are not able to see. So that is how they are deciding amongst their self what to do, what next to do, right? So that is how this autonomy works, right? So I'll just give you 2 minutes. You can probably look into these questions, and then we'll discuss, right? So this will be a kind of revision for you what we have discussed in the guidance part, right? So we'll take a 2 minutes break so that you can absorb what you have understood. By the time, just solve this in your mind, or maybe you can write it on your pen or paper on the chat window, whatever you feel like. All right, so let's start discussing about what's there in this quiz. So, who does the guidance talk directly to? Motors, controller, or batteries? So, the answer over here is the controller, the way we were discussing in the previous slide, right? What is the output of the guidance? So, what do you think? What is the output of the guidance? That is the position, velocity, and altitude. Like we have to go from one position to another. What should be the velocity? What should be the position? So all this, what would be the target position? So that is something which is given by the guidance, right? Loiter is a guidance task. True. So the first guidance command that we discussed about was the loiter one, right? The error vector points from. So this is a bit tricky. So the answer to this is drone points to the target, right? So that is what error vector points to. So over here you could see the error vector is targeting from basically it's looking at from drone to the target, right? So hope till now you would be clear with the guidance part, right? So let's now move to the last what we have to discuss about is the control part. Like so how drone is obeying the physics, how it is appreciating the physics, or how it is trying to work along with the physics such that whatever we want to achieve we are able to achieve. Okay, so why control is hard? So what happens is you have to imagine a scenario wherein you have a cart over here, and then there is one mass which is hanging on this stick, right? So, say for example, you can assume my hand as a card, and this is the over here I place some mass, right? So, what will happen is the natural tendency of this will be to fall down, right? So, it is trying to fall down. So, that is what you know quadcopter is actually doing inherently. I'll not discuss it today why quadcopter is acting like a broom in your hand. How why quadcopter is unstable. So that is a different concept, but naturally the drone has an inherent characteristic that it is unstable. For that purpose we have to have a controller such that it is able to control it, right? Without an active control, for it will flip 400 times a second, right? So it is just telling about the rate with which your drone can just you know it can start spinning and all, right? uh okay, so now we the only thing that I told you is that the drone is unstable and we need a controller to control it, right? So this is a small control hierarchy which is used commonly such that we are able to make a system controllable, right? So for that, let's focus on one of the first on the attitude rate controller. Now, what do I mean by attitude is nothing but our roll, pitch, and yaw. Roll, pitch, and yaw are known. The orientation is known as the attitude, right? So first of all, we require a attitude rate controller. Right? Just stick by me what I'm saying, and then you'll get a feel of it why I'm saying that way, right? So, say for example, you have a drone, right? You want to move in forward direction, right? Now, the drone has the tendency to probably roll, pitch, yaw. It can do anything, right? It is not in our hand. I mean, it is not like if you don't have a controller, my drone will fly like this only. No, that's not the scenario. The reason being, say for example, your drone is going like this, and suddenly a gust comes. So for that, it will flip. The drone has the tendency to flip. For that purpose, we need an active controller. And for that purpose, we are first talking about the attitude rate controller. Our first preference has to be that it does not roll, yaw, pitch, I don't want it to go like this. So for that purpose, I'm controlling the roll, pitch, and yaw. For that, I'm controlling the rates, that is the angular velocities. Clear? So first of all, we are focusing on the attitude rate controller, right? And how we are getting the commands for the attitude rate controller, that we are getting from the position controller. Now, how position controller? Say for example, I want to go in the forward direction. Yesterday, I told you how we can go in forward direction. I cannot simply go like this. I have to increase the thrust of the rotors, or I have to increase the speed of this rotor. Then it will go like this, and then only it can go further. Right? Simple physics. Right? It have to increase the speed, decrease the speed of this, and then only it will go. But how to know where to go and when to go? For that purpose, we have a position controller. Right? So position controller controls the x, y, and z direction. So for example, I'm here. I said I want to go to that position. Right? I have to go somewhere in this position. My drone is here. So what it has to do? It has to turn over here, right? Then it will go in this direction. Then it will go. You're understanding what is happening. Based on what position I said I want to go to this position. My roll, pitch, and yaw are changing, and then it is going. So that is why this position controller helps to give the values to the attitude rate controller, or the attitudes, right? In the simple word, a simple form, if you want to understand in one line, based on what our position is, we are controlling our roll, pitch, and yaw, or based on where we want to go, right? Based on that, we define the velocities. From those velocities, we get the roll, pitch, and yaw. Right? This is the simple analogy I'm giving you to understand how this controller works. And right, and based on these controllers, we give the command to the motor. Right? So increase the for the motor one, increase the thrust. For the motor three, decrease the thrust. So this kind of command is being given to the motors. And what do we mean by state estimate? I told you in the navigation part about the Kalman filter, it is nothing but the estimated states that I'm getting from those sensors, or from the navigation point, such that I'm able to understand what is my current position orientation. Right? I'll tell you, I'll tell you once again in short form what is happening. What is happening over here is, say for example, I want to go from point A to point B. Correct? For going from point A to point B, I know the coordinates of my point B. Now, what will happen is, this position controller will become activated, right? And state estimate will give what is my current position, right? From the current position and where I have to go, an error will come. That error will try to correct such that I'm able to reach that position. For reaching that position, I have this attitude rate controller. I say roll, pitch, and yaw. And based on how much roll, pitch, and yaw I have to do, that command will go to the motors. Right? If you still didn't understand what I'm trying to say, we'll understand it further. No worries. Right? So in nutshell, outer position of velocity loop cascade reference down to inner attitude rate loop. So basically, this outer loop actually determining the inner loop. So that is how it is working. Okay, so let's look at what this boy is trying to do. So what is happening over here is, there is a rod over here, and on the rod, this boy have attached the drone to it, right? So what this controller is trying to do, it is trying to hold it over there, even if the boy is trying to give the disturbance, right? So that is what he's trying to do. See, even if he was trying to give the disturbance, still it was able to hold that particular position. The how it is, or how was it able to control that position? For that purpose, we have something known as PID control, which you have probably might have heard of, and is commonly used for keeping your drone stable. Like how the drone will understand, okay, it's given some error, I have to go back, right? So for that purpose, we have a PID controller. So first of all, we have a proportional P, like PID for all these, what we call terminologies. We have different actions what a drone actually does. So first of all, we have the proportion or the reaction, right? Listen to this very carefully because based on this only our next our next session that is scheduled on Monday is will be affecting based on what we are studying today, right? So I'll take a simple scenario to explain what this PID controller is doing, right? So say for example, maybe I'll take my same drone. This is my drone. I'm at this particular position, right? I have to go at this position. Now, if you see, I have to go at 10 meter. I'm currently at 5 meter. There is an error of 5 meter, right? So what this P proportion will do, it will sense, okay, there is some error. I have to go there. It will start to go over there directly. If I would have been at 4 meter and I had to go at 10 meter, it will go more, right? If I'm at 8 meter and I have to go at 10 meter, it will go probably a bit slow. So did you see what is happening? If my error is high, my P is working high. My P is saying to the controller that I'm very far away. Go fast. Or if uh, you know, I'm very low, drone will say to P or the proportional uh, scenario, okay, I'm nearby only. Just go a little slow. Correct. So that is what this uh, proportional P is trying to do. See, if I'm far away, push hard. Go to that position. Go. So that is what P is trying to do. Okay. So we talked about P. What is the problem in P? You know what? Say for example, this is 10 meter and my drone is over here. It will push itself so hard that it might go above also, right? And then it have to come back. So it will come, right? So due to the inertia, it will go very high and then it will come back, right? So that is the problem of the P, right? So we don't want it to jump like this and then come, right? We don't want it to go like this on 10 meter. Although it reached 10 meter, but it's doing like this. I don't want my drone to do like this. So for that, we have the other components, which we call as the integral. Integral is the memory, right? It acts as a brain for us. So what it's trying to do is based on what was your previous error. Say for example, you have to go at 10 meter. I'm currently at 5 meter. Currently your error is 5, right? Say for example, in the next step, you come at 4. You come at 6 meter. Now your error is 4. This is something that integral actually stores. It stores the error based on the past history. And based on that, it tries to fix. It probably slows down, right? So if P was I'll repeat what P was doing is if your error is high, it will jump very high. If your error is low, it will jump a bit small, right? But what I is doing, I is storing in memory. Okay, now for earlier it was 5 meter error, now it's 4 meter error, now it's 3 meter, now it's 2 meter, now it's 1 meter, and slowly it will go to the 10 meter, right? So based on the memory, it's trying to correct itself and come over here, right? So it acts as a fixer, pushes the drone. Like say for example, there is some wind, right? It goes here, right? Now memory knows now. I was standing at this position. I had to be at 10 meters. Suddenly a wind came and it drifted me. Now it memory know that okay, there's a drift that came. Now my error increased. Now just go take it back to 10 meter. You understood how integral is working, right? So that is how integral works. Then we have a derivative also. What derivative do? It predicts the future, right? It acts as a brake. Now what I mean by acting as a brake is, you remember what P used to do is the error is high, it goes to very high, right? But derivative is something which puts brake, it forces, it predicts the future. Array, what is happening if it is going very, very high, right? So what it's thinking is, what derivative is thinking is, say for example, I'm at 5 meter and now P is acting on this, right? So now derivative is thinking, okay, it means it will go at 11 meter. Let me slow my drone down a bit, right? So that is what that brake is trying to do. It's trying to slow my drone back, right? It's trying to slow based on it feels like due to proportional. What will happen is it will go very high. So that is what derivative is trying to do. Derivative said, okay, I know, I've anticipated that will go at 11 meter. I don't want my drone to go at 11 meter. So that is why I'll put a brake. I'll force my drone to go a bit slow now. Got it? That's the difference between P I D. P is the present, I I is the past, and D is the future. That is how you can remember a PID controller, right? P based on currently what is there, I have to go fast. I based on the past history, it is able to judge. Okay, now I'm going very closer to my 10 meter, so I have to go now slow. And what D is doing, D is saying, I know it will go very high, it will go very fast. Let me put some brake. Let me stop my drone a bit. So that is how the PID controller is actually working, right? So in order to tune it, tune means like whatever PID that I told you, it is not like a one way shot. Like you are able to understand what value of P I have to give, what value of I have to give, what value of D I have to give. You have to tune it. What I mean by tune is, like, you have to play with the numbers, or you have to change the numbers such that whatever performance you want to achieve, you're able to achieve with the help of this PID, right? Say for example, I said my the boy example that I gave in this video. So what it was happening is, there was some disturbance that was being given, right? So how I want my drone to come back? Should it come back slowly? Should it come fast? So that kind of performance, you think that, okay, I want to achieve this kind of performance from my drone. So correspondingly, I give the numbers of this P, I, and D, right? So initially, when you are tuning it, you don't rely on complex math. You rely only on the observation. You just observe. Okay, it's going very fast. Okay, probably I should decrease P, right? P. I have to reduce the P. I have to increase the D. Oh, there is some error. Even after it's reached a state, there's some error. That means I didn't work properly. So I have to increase the value of I, right? So in this way, I'll tell you in next section how to actually tune all this PID control, right? So you don't have to worry about PID if you didn't understand in first go, because anyways you'll get used to it as we proceed further, right? So after the PID controller, we something have known as the control allocation. So what do I mean by control allocation is, we have a drone over here. Now all these four motors are working, but at the same time we have to give them the uh, commands as well, right? That is the job of the controller have to give the commands to the motors, right? So that is what controller does. It tells M1, you work in clockwise direction, but give probably say 1000 rpm. You have to give 1000 rpm. M2, you give 2000 rpm. M3, you give 1000 rpm. You give M4, you give 2000 rpm, but you rotate in counterclockwise. So that is how it the controller gives the assigns the responsibilities. That's the way the responsibility is assigned to different deans of the colleges. Similar way, for the drone, our control authorities are 1, 2, 3, 4 motors. So our controller, which is sitting inside this, it tells M1, you rotate in counterclockwise with this speed. M2, you rotate in counterclockwise with this speed. So this is how this control allocation is being done to the motors, right? Okay, so now we are done with the controller part, and probably now, then take a small little break wherein you can, just ponder upon these questions and how these things are coming, right? So probably we can do it together. So the outer control loop typically handles attitude, position velocity, or motor PWM directly. So we don't directly, handle the motor PWM. Motor PWM is nothing but the control allocation that I was talking about, right? Then remains the attitude and position of velocity. So take it as a thumb rule that for the outer control loop looks into the position of velocity, and inner loop looks into the attitude and attitude rate. Just remember it. Hmm. Then the D term in PID mainly helps in system delay, sensor noise, or overshoot. So what do we mean by overshoot is overshoot means, say for example, the example of the drone that I gave. So my drone is over here and I have to go at 10 meter, but it goes at 11 meter. So that is something we call as the overshoot, right? So what D term is trying to do, it is trying to predict the future that there will be some overshoot. So it decreases the speed of the drone such that it just goes and gets stable at 10 meter. So that is how my D term is mainly helping in the overshoot part. Which axis uses the differential clockwise or counterclockwise torque? Right? So what do I mean by differential clockwise or counterclockwise torque? The one that we discussed in the yesterday's lecture, wherein we said that based on it is rotating clockwise or counterclockwise, we are able to decide that in which direction will it rotate. So for that purpose, yaw is the one which uses the differential clockwise or clockwise torque to, rotate left or rotate right. Right? And then higher P always improves stability. That is false, because that doesn't mean, say for example, you have to go at 10 meter. That doesn't mean that if you have a higher value of P means it will respond rapidly based on the present situation. If I say my error is 5 meter, it will go very fast if I have higher value of P. So for that purpose, it doesn't improve the stability. Correct? Right? So now, we talked a lot about guidance, navigation, and control. But now comes the part of how these things actually works together. Some things I've told you earlier, but now formally we'll be seeing how all these things have been integrated, right? Integrated together so that they work together so that my drone flies properly with stability, right? So say, for example, you have to go from point A to point B. Like, this is my mission. This is the mission that you have given to the drone. Go from this point to this point. Right? This sequence happens hundred of times per second to keep the drone stable and moving towards the goal. Right? So, what is the step one? Sensor measure motion. Right? Navigation. IMU detects the acceleration or rotation, and GPS checks the position. So first step, what is happening is, whatever system is there inside this, it checks what is the position, what is the velocity, what is the angular rate, what is the orientation, roll, pitch, yaw, what is there. The sensor inside this, it actually measures that. Second step, navigation estimates state, fuses noisy data to answer where I am. Here, Kalman filter works, and finally, it gives the states, right? After sensor, there are a lot of sensors there. It culminates what all the sensors are giving, and finally gives you one particular state. One particular state means position, velocities, acceleration. All this has been given estimated answer, so that whatever noisy data we are getting, that is being removed and we can get the accurate value, right? So from there, we are able to understand where am I, right? Then the third step comes is the guidance. Guidance computes references. It calculates error to target and desired velocity, right? It calculates, uh, here I want to go, here is my drone. It calculates what is the error between point A and point B. And like, how much distance I have to cover, 5 kilometer, 10 kilometer, that becomes an error, and the desired velocity, with what velocity I have to go. Then comes the fourth part is the controller. These PID loop convert this error, whatever 5 kilometer, 10 kilometer error we are getting, into the motor mixes, like giving the command to our motors. It'll turn like this, then probably it'll turn like this, and then it'll go. So that is being given. And then motors produce force, propeller spin, physics takes place, and the drone moves to that particular point. So that is how, with these 5 steps, you are able to complete the mission that you want to achieve, right? So this is something that we have studied earlier. I'm showing it again for your reference. How, with the help of sensors to navigation to guidance and control, we are able to control the motors and propellers, right? Timing and latency budget are critical at every stage of this loop, right? So this is the advanced concept which I'm not teaching right now, but I'm emphasized a lot about the update rate. The update rate has to be very, very critical. If the update rate is low for one particular system, it's fast for another system, it will not be able to function properly. There has to be a synchronization. When I want the update rate of one particular subsystem, when I want the update rate of other particular subsystem, and timings. So these things are very, very important to understand. Only then the things will go in synchronization. Otherwise, the drone will go haywire and maybe probably it will crash. Right? So, our last quiz of the day. So, let's do it together. Which role mapping is correct? So, to the obvious answer, navigation is equal to the state, guide guidance is equal to the references, and control is equal to the action. So, that is how you assign the role to navigation, guidance, and control. Which sensor is slow but absolute? So this is a repeated question. So although GPS is slow, the update rate is very high, but it is absolute. Matlab, it gives the exact location of X, Y, and Z. But does guidance tend to control? So I already told you, from the error we get the velocity. How much velocity you want to achieve, how much roll pitch you have to achieve. Right? So that is being given by the guidance. And navigation is a dash sensor fusion. So there was a statement in the slide which told that is a intelligent sensor fusion. So coming to the conclusion part, finally, what we actually understood is, now you know how this drone autonomy actually works, right? So it is not something that you can be perfect in one go. It will take a lot of consistency and effort for you to really understand how these things work, and probably understand all those mathematical equations. You have to experiment on the software as I've highlighted over here. See, these are some of the things that you have to learn to understand this concept of guidance, navigation, and control deeply, right? So one of them is the control theory, wherein probably with the help of MATLAB or Simulink, you're able to understand how PID tuning is done, stability analysis is done. Then for understanding the guidance logic, there's something known as ROS, which will help you to create the path planning, obstacle avoidance, and those kind of missions can be, the logics can be created there. Then we have the state estimation. For that, you have to read about the Kalman filter and how the multiple sensors are being fused. There's a lot of scope in this field, so if anyone wants to go in the drone sector, they can probably look into this. And then we have the system integration. Again, this ROS will help. for understanding how the system integrates and it works, right? So we are done with today. Probably we'll be continuing about learning about PID in the next class. But for today, this is it. If you have any doubts regarding this, or you want me to explain something again, you can let me know. We have probably around 40 minutes, so we can have a fruitful discussion. So thank you for listening to me. Hope you got something new today.
So all the participants who have a doubt, kindly raise your hands. So ma'am, we have our question from V. Denit Uzwal. Please ask your question.
Good evening, ma'am. Am I audible?
Yes, you are audible.
Yes, ma'am. So my question is, what type of material is the drones made of? So the drones are categorized as the domestic one and the military purpose. So what kind of materials are used to prepare those drones, ma'am?
Okay, so for that purpose, generally the material that I've seen most commonly is the carbon fibers. Carbon fibers are mostly used when we are creating these kind of drones. So yeah, it's not like there's no difference between what is used in the industry versus what we are using. Generally, uh, probably the things that are used in the industry are made of the composite materials. We fuse 2 to 3 materials so that we can achieve the less weight and more strength. But generally, if you want to use carbon fiber, is the best option. Next question.
Ma'am, next we have a question from Abhiraksha.
Hello, ma'am.
Hello.
Can you hear me?
Yes, you're audible.
Yeah. Can you repeat the PID one once again?
Okay.
Yeah.
So basically, what actually PID is trying to do is there are a lot of chances that are drone. Say for example, we have to go from one position to another, and it's not directly that we can say, okay, my drone is here and I just go there, or probably I have to achieve 10 meter and I'm at 5 meter. I cannot say, okay, it will go directly like this. This is not something that happens in the real scenario. For that purpose, the engineers or the scientists have created something known as PID. So PID is nothing but the gain value or the numerical values which actually dictate how will my error, the error that I'm getting, will be reduced, right? So that we achieve the what do we call, achieve the what do you call, achieve the altitude that we require. Okay, so say for example, I'll take an example of the elevator, right? The lift that we move up and down. So say for example, you are at 0th floor and you want to go at 2nd floor, right? So now what can happen is, if the controller is not accurate in the lift, what will happen? You might go very fast. You might go with an acceleration that is very high, or maybe your lift is going very slow. It's going from zero, then to first, then to second. It's very slow. So this kind of performance we don't require. And even worse thing can happen if my lift is not accurate, your lift might be stuck in between. It will think I've reached 2nd floor, but it might be some open niche. So that can happen. So for that purpose we have this PID controller. So what this PID controller does is, P means the present, I means the past, and D means the future. So what P is trying to do is, P is trying to say, okay, I have to go at second floor. Probably you can take the example of the elevator. I have to go to second floor. I am at zero floor, but this is my error. That means if this is my error, I have to go very fast. If I am at first floor and I have to reach second floor, I have to go slow. So based on what the current error is there between two floors, based on that, my proportional works. Correct. Then comes the integral. Integral is the past. Like it gives a past value. Say for example, I'm at zeroth floor. I have to go at second floor. It will think, okay, I'm at zero. I'm climbing up. I'm now at first. I'm climbing up. I'm at second. I'm about to reach. I'm about to reach. I reached. Right. So based on the past value, it corrects the steady state. What I mean by steady state is, it tries to keep level with what altitude I want to achieve. If I want to achieve 10 meter, it will try, based on the past memory, it will try to understand and so that we reach at 10 meter, right? Or at second floor exactly, not 10.1 or not 10.2, right? So that is what memory or the integral gain is trying to do. And then what derivative is trying to do is trying to predict the future. Say for example, it's saying, okay, I'm going very fast. I'll overshoot. I'll go up because inertia is there. Due to that inertia, it will go very high. So what this derivative is trying to do, it's trying to say, okay, going very high. I have to slow down so that I can reach. Right? So this is how this derivative is working. If the derivative value is less, there will be chances that it will go high. Right? If the derivative is higher, that means it's predicting the future more. That means it will go a bit slow and probably it will reach the destination it want to reach. Similarly, in the case of drone, right? So I told currently about the PID in a nutshell, but in next class we'll look at the PID controller practically, and then you will understand like how this P, I, and D values are working such that my control is accurate, right? So over here also, if you could see in this, what it is trying to do is over here. See, it's trying to give some disturbance. Due to that disturbance, some error will come, and that error has to be corrected. And that error correction is being done by the PID so that my UAV is stable. Right? I just said in a nutshell. So that is how the PID controller works. If you didn't understand, slowly you just read about it, browse through it, and slowly you'll get hands on to it. Okay?
Okay, ma'am. Thank you. Can I ask one more question?
Sure.
The previous Zoom meeting which happened yesterday, the recorded session is not uploaded yet, and if anyone has missed, it will be a problem to just catch up with the
Mm-hmm.
next session. So it will be better if they upload it as soon as possible. A small request.
Yes. So the organizers could look into this.
Yeah,
Yeah.
ma'am.
Yeah.
Yeah, ma'am. That's all. That's all. Thank you, ma'am. Thank you.
Abhiraksha, you can check the recording is uploaded now, and the date is also corrected. I guess there was some issue regarding the date thing. Now it has been updated. You can check once.
Okay, ma'am. Okay, ma'am. Thank you. Thank you. I didn't check. I was in a meeting, so I didn't check. Now
Okay,
I'll
no
check.
issues.
Okay, ma'am. Thank you so much. Thank you.
Ma'am, next we have a question from Madila Hemant Hariharan. Sorry. Please ask your
Yes.
question.
Good evening, ma'am.
Good evening.
Ma'am, I have a doubt regarding like when we just have a two GPS coordinates, and like if we
Hmm.
just wanted to run our drone in between them like with an autonomous system, like how do we do it with the Jetson Nano 8GB microcontroller? Like we'll be remembering the coordinates inside the Jetson Nano, or what should we do for it?
As far as I know, for this, you have to, if you're not using any GPS, say for example, you're not using any sensor, for that purpose, you have to give the GPS coordinates to the Jetson Nano. Only then it will
Ma'am,
able to understand. But
ma'am,
yes.
we'll be using unlocks UNO 8N, ma'am, for the GPS.
Okay. This For this I don't have much idea, but if you're not using any sensor externally, then you'll have to check the specs of it, whether it have in some inbuilt GPS or not. Any inbuilt GPS
Ma'am, like
system is available or not. If
unlocks is
not,
the
then
system which helps in
Mhm.
identifying the GPS coordinates, and like it will be sending the GPS coordinates to Jetson Nano. And like how
Okay.
to do it autonomously, I have a doubt regarding it.
How do you mean by autonomously? I
Like
didn't get.
without the controlling with the remote, like it wanted to move it around the coordinates which we provided.
Mhm.
Like how
So
do we
for
do it?
okay. Got it, got it. For that purpose only, whatever I taught today, this guidance, navigation, guidance, and control. For navigation, you are sorted. You have this, you're able to get the GPS coordinates. Then come the guidance part. For the guidance part, there are a lot of, you have to read about it. There are a lot of mathematical calculation that are involved. Say, for example, you have to go from one point to another. How do you create the, what do you call, how do you create the path
Path.
mathematically? Then comes the controller. For controller, we have the PID controller. Based on the error that we are getting, like based on the current and the target doesn't mean that you have only one target here, one target here. At every point of time in the guidance, your target will keep changing, and based on your current and target, there will be one error. That error command has to go to the controller. Then comes the PID controller, that how that PID controller will be able to correct the error, and how that correction of error has to go to the motor command. So this is all for autonomous. You have to go into the dwell into the mathematical equation such that you are able to achieve it. So you have to read more about
Ma'am,
this part.
to make a mathematical equation between two GPS coordinates, like there is a classes for it or what?
We will not be covering in this advanced drone workshop, but yeah, so there might be some videos and all that will be available apart from the workshop.
Okay, ma'am. Ma'am, I have one
Yeah.
more question, like a smart one.
Hmm. Yeah.
Like, how do the DJI drones do the track backing, like home back? Like, how do they come back to the location without the control from the remote? Like, they'll be having a green
Oh,
path back of
mhm.
it. How do I do it?
Okay. Yes. So what I this is a good question. So what actually happens is, I was talking about the communication loss that happens, and what do we call it as fail safe. So there are some fail safe modes that are they're available inside the UAV itself. So say for example, what I based on my knowledge, what I know is that when you select when you start your drone, that those DJI drone, it actually captures the home location. The home location is already there with the drone. So what it tries to do is, if say for example there's some communication loss, or from the remote you pressed that return to home, so based on the home location it have already got from the satellites and all, same this guidance, navigation and control works such that it is able to trace back that particular path. Now it is not necessary that it will trace back the particular path, but if it is able to do, then probably it is storing the guidance algorithm as well, the guidance waypoints as well, that from which waypoint it came, and then it comes to that home location, it hovers over there, and then it lands back. So
Ma'am,
that is
will the
how.
data be stored in the microcontroller of Jetson Nano 8GB?
Yes, it will be stored there itself.
Okay, ma'am.
Yeah.
Thank you, ma'am.
So, ma'am, next we have a question from Pierlin Grace. Please ask your question.
Good evening, ma'am.
Good evening.
My question is it possible to increase the update rate of a sensor? And if so, how do we do it?
Okay, so generally it is difficult to update. You have to change the update rate, because whatever is, see, but what happens is, whatever these sensors come from a particular manufacturer. So that manufacturers are the one who have created these accelerometer or gyroscope or IMU. So those are the ones who can change the update rate. As far as I know. So, but when you're designing the drone, it is important that you know at which update rate this particular what do you call this particular sensor works. So that knowledge has to be known. But changing the update rate is quite difficult. Next question we can have.
So, ma'am, next we have a question from Trisha Upadhyay.
Good evening, ma'am. So we
Good evening.
learned that in PID, the P responds to current error and I responds to steady state error. So I just wanted to ask, like, what is the difference between the two?
Okay, so I the first statement was right that P actually basically P, I, and D, they cater to the error itself, right? It's not like I is catering to the steady state error. The only thing is that what I does it minimizes the steady state error. If you increase the value of I, it will tend to decrease the steady state error. If you are currently you achieve the steady state at 9 meter, you are now currently at 9 meter, and you are not able, your error is not trying to compensate for the 10 meter. If you increase the value of I, it will try to achieve towards the 10 meter, right? So that's the only thing that what I is doing, but all the three are trying to minimize the error only.
Oh, thank you.
Okay, ma'am. Next we have a question from Bhuvan Pandey. Bhuvan, please ask your question.
Thank you, ma'am. Good evening, ma'am. Actually, I didn't understand the concept of sensors fusion. Could you please repeat it again?
Yes, sure. So I'll tell you what the problem actually is. So what happens is, we I took the example of IMU and GPS over here. So we cannot trust, in the real world we cannot trust our sensors. Why we are not able to trust our sensors? Because there might be some noise that are available, or it might not be updating the things faster, right? For a drone system, everything whatever we are doing, it is important that things are at the faster pace. If you're from electronics background, the things has to be very fast. Say for example, we are getting the electricity, you know if that is not fast, or say for example our wi-fi, on which we are looking at this Zoom meeting we both are setting. So if that is not at a faster rate, we'll not be able to get the performance correct, right? So there are two problems which happens in the sensor. Now I'll come back to this IMU and GPS. IMU has some advantage and GPS has some advantage, right? So what IMU have advantage, it is fast. It is able to give the values faster, but there are a lot of drift. What do I mean by drift is, since it is converting the mechanical energy into electrical energy, it might happen that there might be some error value that might be given by the IMU. Similarly, in case of GPS, based on its principle that it's getting the position from the satellite, you see on the Google map, how accurate our location is, or wherever you want to go, what are that we get a perfect location. But the problem of GPS is, since the satellites are very far away, there are a lot of delays, right? So we want to utilize the advantage of IMU, also we want to utilize the advantage of GPS also. So for that purpose we have a sensor fusing of the sensor. So what it is trying to do, there is the concept of Kalman filter, which is a mathematical tool which tells the correct state. Since IMU is giving a drift, say for example my drone is at 10 meter, and my IMU is saying that your drone is at 9.5 meter, whereas your GPS is saying that your drone is at 10 meter, right? But IMU is giving data at the faster rate, but GPS is giving at a slower rate, right? So we want to utilize both the advantage. So it predicts the state. It predicts at what state it is and corrects it when new data arrives. So it is just like taking two sensors and just fusing with the help of the mathematical tool such that the exact or the estimated value we get it correct. So just for getting a correct value which is approximately equal to the true value, because in the real scenario, see, in the mathematical scenario, whatever happens is we get all the ideal values, but in the real values, in the real scenario, probably what the Google map is also showing the position, no, that might not be very very accurate. For that purpose we require the sensor fusion such that we get a value which is approximately near to the true value. So that is the simple view of the sensor fusion. If you want to learn more about sensor fusion, you have to probably go more into the mathematics, how the sensor fusion is actually happening such that we are able to get a good values of our position. So that's the thing.
Thank you, ma'am.
Yeah.
Okay, ma'am. So next we have a question from Shantanu Shaw. Please ask a question.
Ma'am, my question is that, for example, ma'am, we are developing drones, so there may be a chance that, ma'am, it may get hacked. It may get hacked from any other different part of the country. Let's say. So for this to reduce this problem, ma'am, what kind of steps should we take, ma'am? Should we make the drone with some specialized kind of material coating or any other thing?
That's a good question. So there are a lot of and that is a practical problem as well. A lot of drones which get hacked, probably due to there is some RF matching, there's some radio frequency matching that they used to get, and they can hack it. So for that purpose, security measure have to be done. One of them, what I've heard of, is the anti-jamming system. You have to inside your drone, you hope I'm audible right now. Okay, so
Yes, ma'am. Yes, got it.
yeah, so in such kind of drones it is important that you have an anti-jamming system such that no other system is able to jam or is able to disable your drone. So for that purpose, these kind of security system you have to do. This is one of them that I remember. Probably there might be other as well.
Ma'am, can I ask one second question?
Sure.
Ma'am, let's say I am asking from ma'am defense point of view, ma'am. Suppose, ma'am, I want to protect my country, so I have deployed some drones in my enemy's territory, ma'am. Right? So, in order
Mm-hmm.
to means not to be get traced to in their radar or their system, ma'am, what kind of material should we use? Like, ma'am, in B2
Mm-hmm.
bomber, which is made by the American aerospace department, so they have used some special kind of material in their coating so that it doesn't get traced in the radar system. So, ma'am, these things can be incorporated in drones if we go in the defense point of view.
Yes, we can incorporate, but there is one problem, in the drone field especially, that you have to look into the weight. Weight plays a very, very critical role. Lesser the weight, the better it is, right? In probably maybe instead of a stealth drone, you can create a drone which moves with more higher velocities and may be able to achieve the mission till the time the enemy territory is able to know whether something has come or not. And then I think there's some I'm not sure. These defense sectors try to use some anti-radar system kind of things also. Like I think that is what our enemy territories were trying to do. So something like this also they try to do. But yes, if you talk in terms of material,
Recently in the ma'am, recently in the upcoming war
hmm,
which is going between Iran and Israel, so Iran had those kind of drones. If I am not wrong, ma'am, it was having some kind of 2000 kilometer range, and it didn't got traced in the American radar system, and
yes,
they
yes, yes,
successfully destroyed that. So as per
yeah.
that,
The,
as if Indians, what we can learn and what we can incorporate in for the future upcoming uh, defense if it is in the drone sector.
hmm, hmm, hmm. In terms
In
of
that
drones,
context, ma'am, I'm asking.
yes, yes, yes. I'm got your point. There's some stealth technology also that is going a lot. If you read about the stealth technology kind of stuff is also something that is emerging, and currently it is applicable for the aircraft, but we can incorporate in the UAV as well. So this is one thing that is coming in my mind. Sorry. Yeah.
Thank you, ma'am.
Yeah.
All right, ma'am. Next, we have a question from King Shuk Biswas. Please ask a question.
Good evening, ma'am.
Good evening.
Ma'am, before I ask my question, can I just give a point to the previous question that the student asked about the breaching of the.
Sure.
Because I was learning in cybersecurity, and there is to breach a drone or any kind of security, we first have to disable the firewall or at least weaken the firewall. So if we can do that by internet or without the internet connection, we can easily successfully crack the whole software and we can use it in our way. Because we actually tried it, just a small timing. It might be 5 to 10 seconds, but we actually cracked that for the 5 to
Oh,
10 seconds. Not
nice.
the
That's cool.
not not so
Hmm.
not a very big tool, but still it is crackable. And my question is that in the current situation, ma'am, we are learning about a lot of things from the American American, not the new American billionaire Elon Musk, that he wants to terraform Mars. And he thinks to if we do this something called terra bombing, it is possible. Now he insisted on doing the drone bombing on that Mars and other planets, so that the people should not have to go there. The drones will take all of the things from the covering spacecraft and just terraform it. So is it possible? Is it possible, ma'am? Because I know it's a very vast topic and it's a very distinct topic from the point you ask, we are teaching us. But still, is it possible to fly a drone outside of a region where the physics of or not the physics, but the condition of Earth environment is not entirely similar to the Mars or any other planet?
That is what scientists are currently, working on. Even I had a chance to work a bit on, such kind of things. There are a lot of challenges that are involved. If you talk about Mars, there are a lot of challenges such as, the density is very low. Although low gravity is an advantage to us, but there are a lot of challenges such as density, temperature values are very extreme. In the night, you get something around probably -60 degree also it goes around. So these kind of challenges are there, and even NASA have tried to deploy a UAV or a helicopter on Mars, which acted as a technology demonstrator and giving confidence to all the nations that yes, flying of UAV on Mars is possible. So one of the research is still going on in India and across the world, so that UAVs can be sent on the other planets. So, and then probably these kind of things will be possible, but it will take a lot of time since Mars is a very long way. So if you understand the physics, anything is crackable. So understanding the physics is important. That is what I could observe from here.
Okay, and it's a bit odd topic from the scene,
Mhm.
but is it possible to create interstellar drones? In
So
interstellar
Elon
drones?
Musk, Elon Musk have already proved the based on the landing of the rocket and landing of its rocket on Makajila, that anything and everything is possible. So currently it might not be feasible for me to say whether it is possible or not, but yes, with the help of proper research, maybe we might achieve something that we can fly a drone in the interstellar region. Yeah, it needs exploration and exploiting the physics.
Wonderful. Thank you, ma'am.
Yeah, thank you.
Okay, ma'am. Next, we have a question from Navya G. Navya, please ask a question.
Yes, ma'am. Ma'am, can you hear me?
Yes, you're audible now.
Ma'am, you previously mentioned in guidance that you have a target and you have a current position. The error is target minus current. So, what if the target is moving now? How can we this guidance work?
Okay, probably I'll go to one of the slide and then we can answer. Okay, so what you're trying to say is like we have a target and we have a current position. We have already decided this is our error and we have started moving, right? That is what you're asking. Hello?
Navya, please unmute yourself.
Yes, ma'am.
Yes. Okay. So basically, whatever I explained over here is, only one step. But actually, in reality, what happens is at every step of time, your error is being calculated, right? So based on your target, say for example, your target is fixed, and but your current is moving at every point of time, due to which your error is changing. Based on what error change is happening, based on that, your velocity value, say for example here, your desired velocity will change. Say for example, you're going from one point to another, right? You're at 10 kilometer apart. Now what will happen, you'll say for example, for 10 kilometer apart, you said your velocity has to be 10 meter per second. Now what will happen is you went closer to, you're going and you are currently closer to this, right? So pause for yourself for a second. Now your error has become 5 kilometer, and for 5 kilometer now your velocity desired might become 5 kilometer, right? So that is in autonomy, at every step of time, even at 1 millisecond, all this kind of computation is keeps on going. It's not like one shot, you understand one thing and you just keep going on, right? So this is how the things work.
Okay, ma'am. Thank you.
Okay, ma'am. Next, we have a question from Kusum Joshi.
Hello.
Hello,
Good evening, ma'am.
good evening.
Ma'am, I did not understand this role pitch and your wala cheese. Yes, ma'am. And the
uh,
update rates, ma'am.
Okay, so role pitching, you're talking about from the previous class or something specific that you didn't understand?
Yes, ma'am. I was not present in the previous class, but also I did not understand the what is state wala slide
Okay, okay, yeah.
and the
So
update, ma'am.
I'll tell you in short, for the sake of time, I'll tell you in short what is this role pitch and yaw. So if you could see a drone, this is one of the drone that I have. So what is happening over here is, so what is roll, pitch, and yaw? We have to change the direction of a drone, maybe in this direction, or in this direction, or in this direction, right? So whatever changes we are doing in this direction, right? That we call it as pitch, right? And if we are trying to roll, right? So this becomes a roll. If along this axis we are trying to change or rotate, that we call it as row. And if we are trying to turn left and right, this we call it as yaw, right? So this becomes our pitch, this is our roll, and this is our yaw, right? If we are going up and down pitch, if we are going this way, it's roll, and we want turning left and right, this is yaw, right? So this is I told you about the pitch, yaw, and roll, right? The one we were talking about. Okay, so now next you asked about the update rate. Okay, so update rate is something that your sensor is doing at every time step. Every time step means that, say for example, here you have this IMU and gyro. Here I said this, it has the update rate of 1000 hertz. Now, what do you mean by update rate of 1000 hertz? Means that it updates after every 1 millisecond. It is giving the data of that, data from that IMU after every 1 millisecond. After 1 millisecond, you are getting the data, right? Similarly, for different sensor, you have different update rate. Here, for the barometer, it has 50 hertz of update rate, which means it updates after 20 milliseconds. So right, in 1 second you get possibly you can say, in 1 second you get 5 times data from that same barometer, telling about the altitude, right? Even the small change in altitude is being observed. Say for example, in first millisecond it is 10.1 meter altitude, then after one update step it is maybe 10.2 meter, right? So that way, small steps, from there you get to know, from the update rate you get to know that how frequently we'll be receiving the data, right? Similarly, for the GPS, it updates after 200 milliseconds, right? So this is what is update rate. Anything else you want me to tell?
No, ma'am. Thank you.
Okay,
Thank you so much, ma'am.
Next, we have a question from Purbhasha Das.
Hello, ma'am.
Hello.
Am I audible?
Yes, you are audible.
Okay, ma'am. I have a question from the navigation section. When you said about the why sensors are not alone, so there was three part of IMU, GPS, and all. So as a solution, you said about sensor fusion.
Right. Okay.
Uh, while using the sensor fusion, can we use AI along with that for better accuracy?
Okay. So I'll tell you about what AI actually does and why we emphasize on sensor fusion. So the problem of AI is that it needs a lot of data, a lot of previous data. It should contain, only then it will be able to tell you that what would be the estimated state, right? So AI may or may not be accurate in this case, whereas when it comes to sensor fusion, when we are fusing two sensors, which are having their own capability. One is, probably giving you better accuracy, other is giving you less accuracy, but it is faster. So by doing this kind of sensor fusion, you might be able to get much better estimated state. But currently a lot of people or a lot of research is going on, like how AI can be implemented in this Kalman filter such that we get more accurate states. So currently, for the simplicity and for reducing the amount of data that we need to store in our microcontroller, we are focusing on the sensor fusion part. But yes, AI might be the future of the sensor fusion or the Kalman filter estimation.
Okay, ma'am. I have another question from previous class. So, as as a MSc student in remote sensing GIS, so can we do the drone specialization or the aerospace engineering or anything? As many sector needs physics and math background. So after MSc in remote sensing GIS, is it possible or do I have to do any specialization on anything?
Can you repeat again, like which specialization you're working on?
In present, I am doing MSc in remote sensing GIS. So if I want to work with drone engineering or aerospace engineering, do I have to do any specialization? Because in many fields, they need physics or math background.
Mm. Oh, that's a cool field. But apart from your specialization, at least it will be better that you get to know these basics of drones, because remote sensing is majorly related. Remote sensing actually relates to the GPS part, but not directly. So, probably you can have a touch upon the aerospace, so that will help you build up the basics, if you want to come in the drone sector.
Thank you, ma'am.
Ma'am, next we have a question from Krishna.
Hello, ma'am. Good evening. Am I
Good
audible?
evening. Yes, you're audible.
Ma'am, you have emphasized that for like some of the concepts, you have to like refer the mathematics from like different resources, right? Like which are the
Yes.
resources you mentioned about, like which we could use, like books or some sites?
Okay, so I didn't include the books for now, but for different there's a book by Randall Beard named "Small Unmanned Aircraft." Other people can also note it down. So this is an excellent book if you want to understand, how drone actually works in a mathematical way. So most of the concepts have been covered over there, which are related to this guidance, navigation, and control. But like one book is not enough if you want to dwell more into navigation. So probably you'll have to take some another book, or for guidance, another. Like say for example, Kalman filter. Kalman filter is a very vast subject. So for that purpose, you might have to look into some probability books. So this is a vast field. So based on that, these books are required. But if you are just starting with the drone sector, I'll recommend to look into Randall Beard book named as Small Unmanned Aircraft. So that will give you a start into how these drones are actually created.
Ma'am, I'm like into mathematics and like general, so like anything for that, not just drones, like aircrafts and all, for that sector of mathematics.
You okay? Just wanted to clarify. You want to know for the aerospace aspect, or
Yes,
you want to know
for the
only the
aerospace,
drones?
the
Okay,
aerospace
for
one.
the aerospace, if you just want to know about the concepts what are being used in the aerospace sector, for that you can recommend a book named Flight Without Formula. This is an excellent book to get you through the basic concept of the aerospace. Then, if you want to go further, there is a book by Anderson, John D. Anderson, named as Introduction to Flight. So that will give you a kickstart into the aerospace sector. So these are the books that you can start with.
Could you just repeat Johnny Anderson's book's name?
Introduction to Flight.
Thank you, ma'am.
Okay, next we have a question from Anandya Sundar Chataraj.
Good evening, ma'am.
Good evening.
Uh, my first question is that I have a couple of questions. My first question is that we use the PID control. Can I please know the math behind the PID?
Okay, probably I'll note it down. We can go more into this mathematics behind the PID in the next class. But if I want to tell you in short, so I is basically the integral. So we are integrating the error that we are getting. And for the derivative, what we are doing, that we are doing the derivative with respect to the time of the error. So simple, in the simple term, this is what is actually happening, and then we are summing all the P, I, and D up. So probably in the next class I'll show you the equation.
Ma'am, my next question is that I thought of designing aircraft which is not obviously unmanned, it is manned, but the aircraft is like flying taxi, but it can move on road like a taxi. It can fly like a helicopter or like a drone, and also it can take speed like an airplane. That means its wings are folded type of structure. I simulated it successfully. Uh,
Nice.
the wings can be folded so that it can fit in the road. Its height is
Okay.
increased, but it can fit in the road. And
Got it.
uh, when it flies, the wings gets
Wings come out.
extracted,
Yeah.
come out, and thus
Yeah.
it can fly. Also,
Hmm.
when it flies and takes speed, there is a thruster which gives it speed or like a airplane. Can we make it in practical? The
Hmm.
combination of drone,
Yes. So what
airplane,
you
and
can do is,
taxi.
hmm. So what you can do is you can create a prototype out of it, and then you can demonstrate it first before you actually create the full model. So I'll recommend
Yes,
that
ma'am.
it will be possible. I feel based on the physics point of view, if your physics are right, you are done with the good simulations, then definitely you go for a small prototype. You try to build it, and then you'll have a proof of concept, like how things are working and if they are working fine or not.
Okay, ma'am. Thank you, ma'am.
Next, we have a question from Shrihar.
Good evening, ma'am.
Good evening.
I already worked with Pizza Hut. Now I am trying to integrate Raspberry Pi with Pizza Hut, ma'am. For the autonomous vehicle, like autonomous drones, is there any common issues can I face?
Hmm. One of them, which is very common issue, is the compatibility. Let's say for example, when you are connecting both of them, make sure that uh, the thing that the one that I told you about, the update rate. One issue is that. Second is that there might be noisy system also, so make sure they are not there. And one is having the baud rate. So make sure that the baud rate between both the system is consistent, like the communication part is done effectively. So these are two to three things. The compatibility is something that you might face, and probably the advanced step would be to validate also whether the value that you're getting is correct or not. So you might have to do some validation test or as well. So these are the three to four things that you have to take care, and you are connecting both of them and then doing.
Thank you, ma'am. Ma'am, and one more thing.
Mm-hmm.
Uh, can we get any personal guidance from you, ma'am, to build like my I have some ideas on developing drones,
Mm-hmm.
but I didn't get any guidance from any others. So can I get any personal guidance, ma'am? Like how to solve my queries like that.
Okay, sure. So what we can do is you can connect me on LinkedIn. We can have a chat over there, and probably based on your query, if you have some advanced queries as well, I can connect you with someone who have some proficient in drones and all. So that's possible.
Thank you,
Shall we
ma'am.
move to the next question now?
Probably, Tanu, if we can have the question in the next session.
All right, ma'am. So, ma'am, shall I end the session now?
Yes, yes. we can.
Okay, thank you, ma'am, for such an insightful session. Thank you all the participants for your patience and cooperation. If anybody has any doubt left, they can ask in the next session. Now you all can leave the meeting. Thank you.
Thank you all.